Well, hello everyone, and welcome back to Adrian's Digital Basement. Who's ready for a little 68K Macintosh repair? That's what we're going to be doing on today's video, where I'm going to take a look at this Mac Plus, which has a burned-in screen, but also a seemingly bad power supply. It makes a whole bunch of clicking noises when you turn it on, and I want to get to the bottom of that and see if this machine works. On last week's video, I took a look at both these machines, and this Mac 512, which had a very sad face when you turned it on. Well, as you can see now, it's working perfectly, so I'll link to that video down below if you haven't seen it already, if you want to see me get this machine up and running. As for today's repair, I'll be working on the power supply in this, or figuring out whatever's wrong with this thing, and I'm going to do it without the benefit of having a second Macintosh that I could swap parts with, because if you're at home working on one of these machines, you're not going to necessarily have extra machines either. So let's try to fix this computer without the benefit of having a spare machine, like I do here, and let's see if we can get it up and working. So without further ado, let's get right to it. So I have to just throw a word of warning before you work on any machines like this, because when you remove the cover, you're exposing yourself to mains high voltages. That is 120 volts here in North America, which can be deadly if you don't know what you're doing. Not to mention when the machine is powered on and working properly, well, then you have the high voltage of the CRT, which also is about 12,000 volts in the case of these machines. So really only take the back cover off and work on these things if you know how to do so safely. Now, as a quick refresher, in case you're not super familiar with these old Macintoshes, this Mac 512 shares the exact same case as the Mac 128, except for a label difference on the back and on the underside here. And the motherboard on this computer lacks SCSI and has larger serial ports, 9-pin serial ports, as opposed to the later Macintosh Plus, where Apple added SCSI to the motherboard and they added little DIN connectors for the serial ports. That means that while lots of parts are interchangeable between these two computers, the back cover is not, really, because of the new layout of these ports. Now, other than the back cover and the motherboard, that's really the only difference between these two machines. The earlier Mac 128s and 512s had 400K disk drives, so they were physically larger and they were also single-sided. But this machine has been retrofitted with an 800K drive and it has the ROMs from the Mac Plus on it. So really, these machines are very functionally similar, except for the lack of SCSI and the difference in the port layout on the back. Where I'm going with all that, though, is if you do have two of these machines and you're trying to troubleshoot problems, you can swap the power supplies between these two machines because they are functionally identical and they will fit and work in either of these machines. But as I mentioned, I don't want to be swapping parts around in this video. We're just going to try to fix this Mac Plus on its own, just like you, if you only had one of these machines to work on. I am actually noticing that it looks like this machine has simply one screw holding the whole case together. And it is this one down here. So I don't know what that means. It might mean that there's not much of a repair video here, because it's quite possible with the clicking power supply that this thing has, that it clicks if the power supply is not connected to the motherboard, which may well be what we have going on here. So this thing is already coming apart. There we go. Just give it a little push and it pops off. Oh, okay, well, there's nothing really to report here. I suppose this is a good lesson for me that I should probably, yeah, so that's not even connected. So I should probably open these up before I try to make videos. Someone has removed the high voltage anode cap. They disconnected the main power supply cable from the motherboard. Floppy's disconnected. Oh, and there's like loose parts in here. In fact, here is the connection that goes from the CRT neck down to the analog board. And I mean, the power supply actually is just sitting in here. So that's a good example. If you try to power one of these up and you don't have everything connected, it's gonna make clicking noises. And I just noticed we have a burn on this connector. This is a very, very common issue. Typically, you have a bad or cracked solder joint on the deflection yoke, and it starts to overheat because you have bad contact, and there can be a decent amount of current running through this connector, and it basically melts the heck right out of it. Now, funny is, on the analog board, I don't see any damage. Kind of makes me think that this analog board was not from this computer. I don't see how it's possible that that connector would have melted like this and not caused any damage on this board. That seems extremely unlikely to me. So I think the best course of action here is I'm gonna take the motherboard out. Let's see if there's anything that looks out of the ordinary on the motherboard. And someone did write something on here. I'll have to take a look at that in a second under better light. But because this doesn't have an expansion board on it, is that a big scratch on the bottom here? You can just slide this right out. So looking at the motherboard, I don't immediately see anything wrong. This is definitely a Mac Plus. I think something just fell off. What was that? Oh, this little metal plate was sitting on the motherboard. So this sits on top of the read-write heads on the floppy drive. It's just a little metal plate. I don't think it's really necessary for it to work, but it does typically fall off. Someone wrote Dan2M, and there are some scratches on this board right here. I think it's cosmetic, and I don't think that goes down to the traces underneath, but that's certainly something worth looking at if this thing doesn't just work when we power it up. All right, so we can slide this thing back in, because I think what I want to do is I want to put the power supply back in the case, hook it up to the CRT. Even though this is burned, this should still make contact. So now what's important is just to reattach the various cables, and you have to make sure to attach the ground lead to the CRT. And unfortunately, someone took that screw out, didn't put it back, so the CRT has no screw there. I'll have to find a replacement. Now, I've had this machine for a while, and you need to be careful disconnecting or reconnecting the anode cap. I haven't used this machine in a very long time, so I'm not too concerned about it. But if you are touching an unknown machine like this, and you don't know the last time it was powered on, it's a good idea to actually short this to ground, which would be any of the screws in the corner here. So you take a clip lead, like a nice beefy one like I have here, clip it onto that ground lead, and just touch the anode button there. That just makes sure there's no stored charge in the CRT. Now, from a history perspective, I don't know where this computer came from, so I don't know why it was left in this state. Obviously, there was no label on the outside to say, hey, this thing is taken apart. So one thing on these Macs, it's really a good idea to ground the power supply board to the main chassis. Now, there's 2 screws here, 2 screws there, and there's even this little metal clip that was just inside the machine. Now, I don't have the original screws for this, so I just used some regular PC case screws and just screwed it in there, and that's good enough to hold that in place. And then there is this little ground lead as well, which you should screw on to the chassis right there. Okay, the mains is connected. I'm going to turn it on the back of the machine. 3, 2, 1. Well, that sounds normal. This might not be any kind of a fix. Looked like it had 1 meg of RAM based on what I saw on the motherboard. Aha, okay, there's no image. So turning the brightness or contrast control, we see no change. Now I'm just gonna carefully lift this up and turn this around so I can take a look. It's dangerous because it is running right now, so it is connected to mains. So just don't touch anything at all while it's running like this. Turning it off, it all sounds normal. Turning it on, beep, just sounds normal. So sounds like the logic board is working fine. We don't know if it's crashed, like due to a RAM error or some other issue, but at least it's giving us that startup sound. Now I'm just gonna unplug this for safety, so stick it over here. When it comes to no image for these original classic Macintoshes, there's a couple things that could be causing that, but the most likely cause is a bad connection or a bad solder joint from the motherboard, the video signal from the motherboard, or on the analog board. It's extremely common with these that is a fault. And I don't know why it affects the video signal the most, but that seems to be the one that's really the most affected. Other potential faults we could have is the motherboard itself could be bad, so it's not outputting a video signal at all. There could be a problem with the analog board. For instance, the cathode drive circuit that takes that video signal and converts it into something the CRT can use, that might not be working, or the CRT itself might be damaged. Another possibility is something's wrong with the deflection circuit, so we don't have any high voltage at all going into the CRT. Now, unless you have a high voltage probe, that isn't the easiest thing to test. I've shown using my phone to listen to the 15 kilohertz scan rate of an NTSC or PAL display, but this doesn't run at 15 kilohertz. I think Macs run around 22 kilohertz or so. Let's try using my cell phone with Spectroid and see if this can pick up. This is a Google Pixel 8. Let's see if this can pick up the sound that this would make while it's generating high voltage. So I'm going to move the scale over to the highest point, and it does seem to be picking up over 20 kilohertz there. Not sure where the Mac is, but maybe it'll be visible. All right, so here we go. Let's see what happens. 22.2 kilohertz. Phone picks it up perfectly. That confirms to us that we have horizontal sweep, and that means pretty much for sure we have high voltage. Now there is another possibility for detecting high voltage, and it's this compact fluorescent bulb here. Now this is a compact fluorescent long tube. The type hasn't been used in a long time, and I think I found this at the thrift store for like $1 or something like that. I'm holding it by the plastic base, but glass is an insulator, so it's okay to be poking around inside the computer, and we're not actually going to be touching anything exposed. We're not touching like the high voltage connection to the CRT. Notice that's not doing anything. The computer is on right now, but look at this. Over by the flyback, it lights up. Neat, right? So if you have one of these floating around, that's another way to see if you actually have high voltage. We turn it off, goes off, turn it on, there we go. High voltage. Now if you're doing this test on something like a color television, that has more like 24,000 volts versus 12 on this thing. I think this is gonna light up brighter than it's doing here. But in this dark environment, we can see that this thing is really generating high voltage. But for me personally, if you know the device you're using runs at a normal scan rate, I think using the phone is an easier option because everyone has a phone and you can download that app, at least on Android for free, Spectroid, and get a good indication if the monitor is working. If the motherboard on this computer was not generating the 22 kilohertz scan rate, you wouldn't have high voltage, but you also wouldn't have any of the sound that you're picking up on your phone. So both methods work, but I personally prefer the method using the phone. So what we know for sure at this point is that the horizontal sync signal from the motherboard is getting up to the analog board, and it is driving the flyback and the horizontal deflection, and that's generating the high voltage. And you need high voltage to have any kind of image. If you don't have high voltage, you're not going to have an image on the CRT. So you can rule that out as a potential problem. The burned connector that goes onto the analog board, that was on, I think, the green wire. And typically the green and the yellow wire is vertical deflection, not horizontal. So theoretically, if this thing had an image, but it had a bad connection on the green wire, you would just get a solid line in the middle of the picture. You need horizontal deflection, like I said, for high voltage, but the vertical deflection is a separate system and it's not required for the image to work or display. Obviously, a line is not a working full image, but it tells you that the whole CRT circuit is working. Now, besides the high voltage, which we know is working, and the cathode drive, which drives the cathode to display an image, which we haven't tested yet, the other thing you do need is you need filament voltage. So you need 12 volts on these little 9-inch CRTs to be going to the filament, and that creates a little bit of a glow inside the neck, and that heats up the cathode that allows it to be emissive so that you have an image. So a good test you can do is, again, turn on the system, turn off all the lights so you can see into the neck, and we need to look to see if we actually have a glowing filament in there. So hopefully this shows up, but I am pointing right to the glowing filament right there. If I turn off the monitor, it should go out. We turn it back on, it should be visible, I think. It's very hard to tell on the camera screen. I'm looking just a little tiny LCD screen. Hopefully it's there, but I can definitely see the filament glowing. So that tells me that 12 volts is getting from the analog board to the CRT. That's one of the other components required for this to work. Now, another possibility is the CRT was used up within an inch of its life. It just doesn't work anymore. But we need to rule out all the other possibilities first before we jump to that conclusion. Oh, and we say we need to swap out the CRT. Did you see what just happened when I touched the screen? Looks like when I tap the side of the computer, I see for a split second, the disk icon appear. So that tells me that we have a bad solder joint. I'm gonna move or wiggle the power cable that goes to the motherboard. I saw it for a second. There it is. Okay, so this machine has a fault, by the way. Besides the fact that we have a bad solder joint, where's the gray background? It's just not there. The CRT is very dim, it's maxed out right now, and we just have the flashing disk icon, but we should have that full gray background. And to show you what I'm doing, I'm just pulling on the cable like that. I was pulling towards the back, and that made the disk appear. So that definitely confirms that we have a bad solder joint. Now, if you have one of these Macs, the 128, 512 or plus, and you have no image, but you have a normal sounding machine otherwise, I really recommend you reflow the pins on the bottom immediately. Just do that right away, just to skip over the troubleshooting I just went through. I wanted to talk through all the various possibilities just as a thought experiment, because it's really good to analyze the evidence that you're looking at when you're working on one of these machines. But it's such a super common problem that this pin right here that I have my finger on, that's the video input pin, gets a fractured solder joint. So it's a really good idea just to reflow those right away just to save yourself some effort if you're not trying to go through all the troubleshooting steps that I'm doing here on this video. So those are all taken care of on the motherboard. That probably will fix our issue, but I've definitely run into plenty of problems on the analog boards where it's also a bit of an issue. Now this analog board is actually stuck down with this double-sided adhesive. Kind of annoying, but it just is what it is. This is the connector that goes down to the motherboard. I'm gonna reflow that. These are the 4 pins that go to the deflection yoke, the one that was all melted and burned. So I'm gonna reflow that. And then this row of pins is the connector that goes to the neck of the CRT. You wanna reflow that one as well. And because this double-sided foam is on top of the pins that go to the deflection yoke, I'm going to scrape it off a little bit. But I can tell you, looking at this, I don't see any evidence of browning of the circuit board. Typically that kind of heat to melt the connector is going to cause this to turn brown a little bit. And that has not happened. So it's my honest opinion, this analog board is actually not the one that was in the machine originally that burned. Someone swapped it out and for some reason never went through with the complete repair. They never put it back together all the way. I can see that these are actually cracked though, these joints here. So while it was making an okay connection, if you have issues here, you get like weird geometry problems with the CRT, kind of goes in and out. And then you have heating of that joint, especially on the horizontal pins, which can cause that melting. As for this plastic sheet, you can just reattach with some new double-sided adhesive or hot glue. Typically what I use is just some hot glue, and that holds this in place. For now, we'll just stick it there. It's my assumption after reflowing those joints, this machine will just work. So let me just turn it on, 3, 2, 1. It's going to look dim because the CRT is worn out, but that is just par for the course. Oh, there it is. Now, like I said, where's that gray background? So we definitely have a fault on this machine. We definitely have a fault. I'm going to push the reset button. Oh, I went to go push the reset button, and right away we got a SADMAC 0F00D. That's not a RAM fault. That's actually the code you normally get when you touch the interrupt button, but I hadn't yet pushed it when it showed up. I'm just feeling the buttons without pushing them. Oh, that's the reset button, obviously. Yeah, interrupt button, I'm just wiggling it. As soon as I push it, we get F000D. Yeah, interesting. And the F code, if we look it up, I think just means interrupt button pushed. So that was weird that it showed up on its own. I'm just going to bump the computer. So I'm just hitting it with the rubber end of my screwdriver here. See if any kind of faults happen here. Pushing on the wires. Yeah, image is stable. It's looking good. It's not doing anything strange other than the fact that we don't have the gray background. So for testing to see if this thing even boots an OS, which I don't think it will, I'm going to plug in the floppy EMU, and this is emulating the floppy drive hard drive right now, just like I was using on the Mac 512. Even though this machine has SCSI, it does support booting off the floppy drive based hard drives that Apple made. So let's turn this on. Pretty sure this thing is going to crash as soon as it tries to boot an OS. I mean, it's got the Happy Mac, but that's it. It's stuck. And if I look at the floppy EMU, this LED there is the indicator LED to show that it's doing something. But it's like the OS has booted up, but we're still stuck at the Happy Mac icon. So I have a suspicion as to what's going on here. Because the interesting thing is, we have the Happy Mac. It seems like it booted up because I saw the normal activity on the floppy EMU. But here's something interesting. If I push the interrupt button, we don't get anything on screen. There's no evidence that anything was actually happening here. Now, if I push the reset button, resets the computer normally. We don't see that gray screen. We just saw the floppy, insert floppy disk icon for a second, and now we have the Happy Mac, and the system is booting back up. Now, one thing that's interesting about these original classic Macintoshes that go all the way back to the original Mac 128 is Apple designed this with 2 separate screen buffers. So even though the first Macintosh had very limited RAM, they decided to allocate an entire screen buffer twice, I think to facilitate animation where you could switch in hardware between the 2 screen buffers. So it's sort of double buffer, right? You could draw your stuff on the second buffer and then switch to it and go back and forth to facilitate that nice smooth animation. My hunch is what's happening here is that this machine is stuck on the wrong buffer. I think for reasons that, well, maybe are because this machine has a fault like this, when the system first boots, it actually draws the icons on both of the screen buffers. That way, if you're stuck on the wrong one, which I think this machine is, what you're not getting is that checkerboard background. You're just getting the icon, and now that the OS has booted, it's drawing to the other buffer entirely and exclusively. That way, nothing seems to be updating on the screen anymore. My hunch is that this machine is fully operational right now. We're just looking at the wrong screen buffer. Now, over on BitSavers, there's a copy of this document, the Macintosh Hardware Map, confidential, from 1983. So this is talking about the Mac 128, but the Macintosh Plus is similar enough that all the information we need to figure out how to check to see if this thing is stuck on the wrong screen is in this document. Now, since this machine has a Motorola 6800, the Motorola 6800 supports 16 megabytes of addressing. And on page 3, we actually can see that entire map. So it starts at 000000, and it goes all the way to the top here, which is FFFF. Now, one thing to keep in mind is when you power up a Macintosh, there's something called an overlay, which is enabled by default at power up. And what that does is it maps the ROMs to the beginning of the address space. And this is common to all Motorola 6800 based systems. The Amiga is the same way because the 6800, when you first power it up, it starts to execute code from the very bottom of address space. Now, what's typical is with these systems like the Amiga and the Macintosh is once it starts to execute code out of the ROM, it sets a flag in hardware using one of the VIA chips on the motherboard, and it remaps the ROM up into some other spot in memory, and it puts the RAM down at the bottom of the address space. And that's called the overlay. And when you look at the normal memory map with overlay 0, this is the normal memory map, which for the Mac 128 is 128K, and it starts at 0000. Now, these classic Macintosh, and I know I've talked about this before, they support exactly 4 megabytes of system RAM. The reason why it can't do more is not because of the address space, it's just this memory map that Apple picked stuck the ROMs physically when the overlay is turned off at the 4 megabyte boundary. So that's where the ROM sits, and there is a bunch of space for additional ROM space above that. Notice how it has 64 kilobyte ROMs, and then there are 15 ROM images. So the ROM select logic is actually pointing to the same ROM chips for all of that space, but because there's only a 64K physical, at least on the Mac 128, it just replicates it over and over again. And for the RAM, it's exactly the same. So the 128K starts at the beginning of address space, and it repeats over and over again all the way up to, well, the top of that 4 megabyte memory space, which is 3FFFF. And the 128K just repeats over and over again throughout that range. Or if you have a 4 megabyte Mac Plus maxed out with all the SIMs, then this entire address space is filled with RAM, physical RAM that is, and there's no repeating. Now, the reason why this is important is because if we keep looking down this document here to what's in the memory space, here it is, the map of RAM. If we look up at the top, we can see the video screen, page 1, bottom and top. And you can see when the system boots up in the overlay mode, that's the initial power up phase, it's at 61 A700. But then once the overlay is turned off, which is normal operation of the computer, the screen buffer is physically stored in the 128K of RAM on the original Mac 128 at this address, 01 A700. Now, if you're going to write to that screen buffer 1, we have to remember that I just said up here, if we scroll back up, that the memory repeats 31 times, all the way up to the top of that 4 megabyte space. That's a hardware feature of the way the RAM select logic works on this thing. It just repeats it over and over again. So if you're writing to the screen buffer, you don't actually have to think about how much memory is physically installed in the computer, because if you have 128K on a Mac 128, or you have a full 4 megabyte Mac Plus like the one we have sitting here, instead of writing to 01 A700, which is the physical location of the screen buffer in the RAM, on the 128 that is, you can write to 3F A700, which is one of those mirrored copies way up at the top, or on the Mac Plus that's fully maxed out, or any other of the classic Macs that has 4 megabytes of RAM, that is the physical location of the screen buffer. But if you have a 2 megabyte Mac Plus, the top of memory is 1F FFFF, and you can still write to the screen buffer at 3F, the same place as the 4 megabyte machine, because of that mirrors. That 2 megabytes of RAM is mirrored again just once above it. Anyways, long story short is you can always write to the screen buffer 1 by writing to 3F A700, and if we look down here, there's a second video page, and this one exists at 2700, so it would be 3F2700 if we want to write to that. Now, I was perusing this documentation a little bit because I couldn't exactly remember how the screen buffer is controlled, but it looks like it's controlled by this VIA 6522 at U15D, at least on the Mac 128, but on the Mac Plus will be the same. And if you look here, there it is, video page 2, it's PA6 is the output, and that tells the PAL chips that are on the motherboard, which generate the video, which part of memory to look at to draw the screen. And the output of this signal, when it's 0, we're going to be looking at video page 2. Well, I happen to know when you first power on the VIA, I'm pretty sure that the output of PA6 will be set to 1 by default, and the ROM code that's executing needs to change that output to be set to 0, and that'll switch the video to page 2. Now, I don't really know when these Macs are just running normally which screen buffer is being written to, but my feeling is there's something wrong with the output of this chip, like it's stuck, or there's a bad trace, so into the gal chip, or maybe the gal chip itself that handles this is also bad. I mean, there's a few things that are wrong, but we can obviously look at this signal and try to see which one it's writing to. If we take a look at Notepad, I've typed out a few things in here, including here's the total address space, 4 megabytes. So like I said, it goes all the way up to 3F, FFFF, right? That's the top of that 4 megabyte space. So screen memory 2 start address would be 3F2700, or screen memory 1 would be 3F A700. Well, if this machine is actually running the OS right now, I can push the interrupt button and I should be able to use the Microbug. That's the thing that pops up on a Mac when you push the interrupt button to physically write to screen memory. And we can write to both of these buffers here and see which one of them generates pixels on the screen of this computer. Now, it'd be logical, at least from me, from a designer, that if I had 2 video pages, that I would default to using page 1 for normal operating system activity, and it would be page 2 that would be not generally used unless a program wanted to do animation or something like that. So going back to my notepad here, that would imply if I write to anything in this address space here between A700 and FC00, nothing should show up on the screen of this computer. But if I write to the memory in this section, 2700 and up, I think it's going to show up on the screen of this computer. So I happen to know from previous experience, but just this would be the way I would design it too, is that the screen buffer on the Macintosh is just linear. When you write to the first address in the address space, the pixel that would turn on is up here, and the last pixel in the memory buffer would be down here in the bottom corner. So what I'm going to do is I'm going to push the interrupt button. Okay, I pushed it, and I have a keyboard connected up to the computer. And I think that this is screen buffer 2 that we're looking at. Now I'm going to type SM for set memory, 3F2700. So that would be the first address of page 2, and that would be a pixel up here. And I'm going to write 5555. I'm just going to type out a bunch of 5s because that would be alternating pixels. I don't know which pixels are black and which are white. Like if it's inverted, like if I wrote all Fs, would that be black? Or all 0s, would that be white? Or vice versa. So I'm going to do 5555, 5555, 5555, 5555. Sorry, that's kind of boring sounding, but let me hit enter. That didn't do anything. Now, one of the problems is I'm operating blind, right? Like I don't really know if I typed that correctly, and I probably should just type it again. So I push the interrupt button again, SM34 or 3F2700, and we'll do 5555. I'll just do it once. Okay, nothing showed up at all. Right. Just in case, I'm going to push interrupt again. I'm going to do SM for set memory, and I'm going to do 3F A700. Sorry, I know you can't see it. And we'll do 5555 again. Ah, pixels just appeared. So we are on screen buffer 1 right now, not screen buffer 2. Let's do that again, but I'll write some more pixels to it. So SM34A700, and I don't know, I'm just going to write 0000, FFFF, 0000, and FFFF. Ah, yep, okay. Does that show up in the camera? I think it does. I can see it on OBS there. So we have 2 white dashes. Now I typed in 0000 and FFFF, so that tells me that when you write zeros to the screen buffer, that shows up as white pixels. So we could actually do that again, but I'll move it a little bit over to somewhere else on the screen. So we do SM for set memory, 3FA7, and I'll put like, I don't know, 50, and 0000, 000. I don't know if I typed the right enough zeros, but there we go. I drew a white line further over because I offset the memory location I was writing to. All right, this is telling us some really important things. First of all, I know that the computer is booted up into the OS because the whole Microbug environment is working. That doesn't work unless it's booted into the OS. The second thing I know for sure is that the circuitry that generates the video is reading from screen buffer 1, but for whatever reason, the OS, other than the little Happy Mac, is writing, I guess, to screen buffer number 2. Now, I suppose what I need to do is try to figure out how I could change to screen buffer number 2. Now, that involves altering the output of PA6 on this VIA. Or maybe what I should do is I should just probe PA6, whatever pin that is, and we should look at the output. If it's 0 or low, that means we're going to be looking at video page 2, which obviously is what the OS expects you to be on. Or if the output is high, that means, well, that would be video page 1, which is what we're looking at right here. Now, if I look at PA6 and the output is low, which means it should be video page 2, which I assume is what we should be on right now, then maybe there's a problem with the GAL chip or the PAL chip that's generating the video, like the input wherever the signal goes, or there's a bad trace. Now, I don't know where this file came from. I have some early Macintosh schematics that have been recreated because they're actually easy and clear to look at. I don't know who made these. Don't think there's any kind of names on this, but I have this saved onto my Google Drive because it's quite useful to have something that's clear and easy to read because there aren't really good schematics that I've ever found for these old machines. So if we look at the 6522 that's generating the signal we're interested in, it also is handling sound volume and real-time clock. And it looks like it is this one on the schematics because there's a real-time clock. I'm assuming there's some sound volume stuff, and it was PA6 that we're interested in. So that is pin 8. And if we follow that on the schematic, it goes way over here. Come on, hello. Oh yeah, video page 2. There it is. And that goes directly and only in to pin 4 on U4G. And I'm assuming U4G is a 74AS253. I have to go look up what that is exactly. So just taking a couple notes here. U15D, that's the VIA 6522. It's PA6, that's the output or the IO pin. Pin 8, that goes to U4G pin 4, which my assumption is that's a 74AS253, which is actually 4 of 1 data selector multiplexer with 3 state output. I'll keep the truth table handy just in case we need to analyze what's happening on that chip. If we see the signal going into that chip and everything looks good, it could well be that there's some other condition that's happening on the truth table that is not being satisfied, that is creating the incorrect output. So as my assumption right now, the problem is either a bad trace, because we saw those scratches on the bottom of the system, or this VIA is not outputting the correct signal that goes to the multiplexer. Or the multiplexer itself is bad, it might have a bad input. So here's the Mac Plus motherboard. I have the multimeter and continuity mode. Let's just first check to see if there's a connection between the VIA at U15D. Well, there's only one VIA, here it is. Now, the numbers must have changed between the Mac Plus and the other ones because there is D, so it's 15D. Well, there's D, but it only goes up to 11 on the numbers right there. So anyways, we know it's pin 8. There's 8, and the one we're looking for is at U4G, so there's 4 and G. So there's a 74F253. I don't know for sure if it's that chip, but let's see if it connects to pin 4. Ah, it does, and we have good continuity there. Now we do know that there are some bad traces on the back here. Let's take a closer look at these. Obviously something happened to the system. See how these pins are bent over? So some kind of a large scuff. Did that cause any of these traces to break? Let me just quickly tone these out. So that trace is good. It's this trace right here, and then the one below it goes from there all the way over to here. That's fine, so there's no break in those. And what about these? These look a little bit worse there, don't they? I think it's gonna be fine though. The top trace, which is definitely exposed, that makes its way here. That's fine. And the one right below it, that goes from that VIA to there. Okay, so that's fine as well. So those 2 traces are good, those 2 traces are good, and these don't look bad enough. But you know what? I've been burned before where I thought everything looks fine, and it was actually worse than I realized. So let's go from there. That would be this top trace. Looks like it goes to there, and that's fine, no problems. And let's see, where's this one go? It goes from that VIA to there, that's good. And this is one of the memory slots. Goes to there, and it's fine. Okay, so that's not actually bad. Just for fun, to protect those exposed copper bits right there, just gonna put a little bit of nail polish on there. Oh, look, it allows us to see it a little more easily with the nail polish on it. But yeah, nothing was broken there. And we know we had good continuity from pin 8 on the VIA going to that IC over here at U4D. So this looks good. Now what I think I need to do is power this up, and we need to look at the output signal coming from the VIA. This still could be a bad VIA, or the multiplexer could be bad, one of those two chips. So let's take a look at the signal with this powered up. I went ahead and used a Sharpie to mark the pins. We're looking at that one there, that one there. That's the two pins that are relevant. I put a little piece of plastic here just to make sure that the mains is kept away from the motherboard. And I have the scope out. We're just gonna be using this one here. Let's turn on the computer. Okay, everything sounds good. I'm just looking over at the screen. Yep, okay, we have a flashing question mark, but we do not have the gray background. On the input to this IC, it is high. Now I'm gonna power cycle the computer. Let's see if it does anything different. When we turn it on, it just goes high immediately. And according to the information, that signal when it's high is video page 1, which matches exactly with what we were seeing. So A700 is video page 1. And remember, that's what we were writing to in the Microbug. And based on the output of the VIA, it is page number 1 that's being selected in hardware. The actual hardware is looking at the correct location in memory. Now, here's what's confusing to me. If the hardware is selected to page number 1, and when we write to that part of memory, we're getting screen buffer number 1, why isn't the OS writing to the screen buffer correctly? Obviously, when the system initializes, it writes or draws the Happy Mac and the flashing icon correctly, but the checkerboard pattern's not being drawn correctly, and nor is any of the OS. Where is that going? Where's that being written? Now, I just had an interesting thought. What if the memory on this machine, where it looks like it has 1 megabyte, it has a problem? And when the ROM is initializing the system and doing the initial phases of the RAM test, it detects the memory, which I think is the very first thing it does. It tries to figure out what the top of memory is, and it does that by looking for those repeating images of RAM. So it starts to write to locations in memory at these boundary marks, and when it writes to one and it sees a lower one got overwritten, it kind of considers that the upper boundary. What if it's detecting, for instance, 512K of RAM on this system, not the full 1 megabyte, which it looks like is installed on the board? And when ROM figures out what the top of memory is, it writes a pointer into the memory somewhere. And I think the OS, when it starts to boot, or maybe the ROMs or whatever, when the system starts to boot, it looks at that pointer, and then that helps it determine, okay, yeah, that's the top of memory. Well, it's quite possible that when the OS writes to the screen buffer, instead of writing to that mirrored copy all the way at the top, which we know works, because when I wrote to it directly, we saw updates on the screen. What if it's writing to the actual screen buffer that it thinks is the top of memory? So what I mean is, for screen buffer 1, the offset is A700, but if we're writing up on a 4 megabyte system, to write into physical memory, you would write it into 3F A700. Well, that's what I used with the Microbug, but that clearly was using one of the mirrors of memory, because this system only has 1 meg of RAM based on what I see on physically installed on it. But what if the OS is using that pointer to actually write to what it thinks is the top of memory? Well, if the system is thinking that this computer only has 512K of RAM, well, instead of the upper boundary of the physical memory being FFFF, it's actually going to be 7FFF, which is 0K to 512K. And that means it's going to be writing to, what is it going to be writing to? 0F A700 for the screen buffer, instead of the actual screen buffer, which is 0F A700, because there's physically 1 megabyte on this machine. I just don't know enough about the Macintosh OS to know if it writes to the mirror address up at the top, that 3F A700, or if it's using the actual physical address based on the detected amount of memory on the system. Now, from a thought experiment, if a system detects more physical memory than is actually on the system, so say it only had 512K, but it thinks it's got 1 megabyte, that will definitely crash the computer. And that's because that 512K is mirrored, so there's 2 copies of it. So when it goes to write something in the upper area, it's going to overwrite the stuff in the bottom area. But there's nothing wrong with it detecting less memory than physically exists. So 512K versus the 1 megabyte that's physically on here. The only side effect of when you do that is that the mirrors become affected because the 1 megabyte is mirrored 4 times because there's 4 megs of address space, but the 512K should be mirrored 8 times, but it's not because physically there still is 1 megabyte of RAM on here. So when it's writing to the screen buffer down in that 512K, instead of it being mirrored up to the top of memory where the hardware reads out the actual RAM, it's being written to in the wrong physical area of the RAM. Now, there's a couple reasons why this thing may be detecting the RAM incorrectly. We just might have bad RAM on the motherboard. There's an absolute real possibility that the RAM is just bad on here. I think there are some jumpers on here somewhere. Allow me to select how much memory is actually on the system. The jumpers are required because the system needs to be told how much RAM is on here, and that's what creates that mirroring, right? If it's set to 1 megabyte, but the system thinks with the ROMs, think there's only 512, well, the jumpers are still configured for 1 megabyte. So that means the mirroring is only going to be set up for, what, 1 megabyte boundaries, right? So 4 copies. If I could set the jumpers to 512K, even if I have physically 1 mega in here, that doesn't matter. It's only going to select 512K from the RAM on here, and then it's going to mirror it 8 times, which means the video should start working if I change that jumper appropriately. Here are the 2 resistors that select the amount of RAM on the system. So R8, R9, one says 256 kilobit and one says 1 row. I think this one, when it's installed, tells the system that it is 256 kilobit sims, which is actually what's installed in this system. I think this one is installed to make it think it has 512K. It's only got 1 row of memory. I have to remember this is a 16-bit system, so 2 sims at a time. So first, let's just see what resistor value this one is that's been cut already, 150 ohms. All right, I went ahead and I installed a 330 ohm resistor. It's close enough into that other position, and that one is resoldered. So let's see what happens with them configured this way. I think this should result in 512K. I looked online and it didn't seem like 512K was a supported configuration. I don't know. What are we gonna get? There we go. It freaking works. I have a feeling the problem we're actually having here is that the memory that's installed on the board is bad. Okay, floppy emu is connected again. So yeah, I think it's bad. So like my hunch was, it was detecting it only as 512K while the motherboard thought it had 1 megabyte. Therefore, it was writing to the wrong area in memory, which is why we weren't getting anything. Let's turn the brightness down so it doesn't blank on the camera. My hunch is that when we look now, once this boots up, it's gonna show 512K of RAM. And yes, it does, 512K. All right, so my hunch was correct. It was just writing to the wrong screen buffer. And I guess I haven't run into that particular issue, at least on the Mac Plus, where there was bad RAM that wasn't detected with like a sad Mac or a crash, and yet you got no actual usable video. So that's pretty interesting. Now, it is my hunch, if I replace the memory on this machine with 4 megabytes, that it will still think it has 512K based on the way I have those jumpers configured. And I'm also curious, because I looked online and people were saying, oh, you couldn't have 2 megabytes of RAM on one of these machines, but I think you can actually, and let's give that a try. You know what, actually, just for fun, I went ahead and removed the first 2 memory modules that were closest to the edge of the board towards the front, that is, where the keyboard connector is. I think those first 2 memory modules near the front edge are used for the first 512K, so I don't think the system is gonna work at this point. I mean, the beep sounds normal, didn't it? No, it is working. Okay, so the 2 memory modules that are used for the first 512K are the 2 that are closest to the CPU, so they're facing the back of the machine. So if anything, it is these 2 memory modules which are the bad 2, because remember, it should have had 1 megabyte, but it wasn't detecting 1 meg when these 2 were installed. But obviously 512 is totally fine. Now be very careful to remove these modules, because we know these SIM sockets are like the Break-O-Matic variety. In fact, oh yeah, it's already broken. The SIM closest to the CPU already had a broken clip. So if we turn this on now, yeah, we're just gonna get garbage. And it's not gonna beep because that's required. You need to have RAM. And we should have a bunch of garbage. Actually kind of cool, we have like a interesting repeating pattern. Kind of neat. Okay, I found 2 1 meg modules. I'm gonna install those closer to the CPU, so toward the back of the machine. Okay, here we go. We got a beep, and it's gonna work. So it's telling us that the main memory is at least recognized. Is it gonna see it as 2 megabytes, which I think it will? I would say so, yes, because see, this RAM test is taking longer than it normally would. Now, the odd thing is I would think that if it is detecting this as 2 megabytes, that I would have needed to remove the jumper or the resistor that said 256 kilobit. What do we actually get? We do have 2048K, so it is working. I don't really know what that resistor that said 256 kilobit is for, other than maybe that one determines if the system has 256 kilobit memory modules in the second 2 slots. Yeah, not too sure about that, but system is still working. It's booted up. It's got 2 megs of RAM now. And I suppose the ultimate test to see about these 2 memory modules, these are the 2 that were towards the front edge of the computer that I removed first and didn't really change anything. My hunch is that these 2 are bad. One of these is going to be bad, one or both. So I suppose for completeness, and if I break the SIM sockets, I'm going to be kind of annoyed, but I'm going to take out the 1 meg modules that I put in here, and I'll stick in these 256K modules. Okay, they are in. Let's see what happens. No. We got the bong as normal. Wait, they work too? Must have just been a bad connection. Yeah, that's the only explanation there. We just had a bad connection on the SIM slot. That was causing this not to work. Actually, I just had a thought. Maybe the memory modules weren't bad at all, and there's a bad trace. Remember that scratch we saw on the bottom of the motherboard? What if it's causing a bad trace, and those 2 SIM sockets that are near the edge are actually not working? Well, let's put in these 1 meg modules here, the ones that I know will work. And I'm going to lift up the resistor that I installed that says 1 row, because that's the one I think that makes it 512K or 2 megabytes. I'm going to lift that one. Okay, so let's see what happens now. So we have 1 megabyte installed again with the original memory modules. And then I lifted the jumper that says 1 row. It's the one I installed, 330 ohm resistor. But I do have the other jumper connected that was originally cut that says 256 kilobit. So let's see exactly what that does. If we're back to the original problem, like those 2 SIM sockets are bad, then no. System's fine. And my assumption is if we go to About Macintosh, we should have 1 megabyte of RAM, and we don't. We have 512K. Well, I have to admit, I'm a bit surprised here. I don't really get it. The memory modules are swapped around, so the 2 that were closest to CPU are now closest to the edge of the motherboard, and vice versa. So where's the rest of the memory? And I guess what's weird is in addition to that, we have a working screen. So we don't have the same problem we had before where there was physically 1 meg of RAM, but the OS was writing into the wrong spot because it thought it had 512K. The system thinks it has 512K, but it's repeating correctly, which is why it's actually writing to the screen correctly too. I really have to imagine that, I'm noticing this memory module near the edge is kind of warm. I have to think there's a problem with the SIM sockets, but just to make sure, I'm going to swap out all the memory. I'll put in a different set of 256K RAM. All right, a fresh 1 megabyte has been installed. No additional clips were harmed in the installation of that RAM. Okay, so we have working video at least. Good sign, good sign. Right, we are still stuck at 512K. I think there's a problem on the motherboard with the RAM sockets. It's the only thing that could explain the behavior. I think the only other thing I'm confused about is why haven't we gone back to having non-working video though? Maybe what I need to do is lift the other resistor, the one that was already lifted when I first tested this machine. Okay, now it's back to the exact configuration it was when we first started. Of course, the only difference being I have 4 good memory modules in there. Look, and it's freaking working. So I wonder now if it's going to show us 1 megabyte of memory. No, it still says 512K. It still says 512K. I don't understand. I don't get it. We're right back to where we started, except that I have the original memory out of the system, but it's not detecting the 1 megabyte. I just don't get it. There's got to be a bad connection or something on the second SIMs, but why do we have all those video problems originally? I bet you there's people watching who have a lot more knowledge about these Mac Pluses than I do, who probably have an idea about what's going on. All right, so it's getting later in the day. I'm gonna have to take a break and think about this a little bit and regroup and try to figure out what's going on and why I can't see all the memory. Another day, we're back on the Mac Plus, and I have something to show you. If we turn on the machine, the motherboard, by the way, is sort of propped up back here. You can just see the edge of it. So this is the RAM test screen on these classic Macintoshes. You get these diagonal lines across the entire screen. And it's sitting here and taking quite a while. The length that you see this screen is an indicator of how much detected RAM the ROM is finding, because the more RAM, the longer the RAM test, and the longer you see that pattern. When you have just 512K of RAM, that pattern only appears for a split second before you get the Happy Mac as it boots the OS. On the motherboard, I've gone ahead and I removed the 256 kilobit RAM that was in here, and I installed 1 megabyte SIM. So this thing has a total of 4 megabytes. I wanted to do this further troubleshooting with all the RAM installed. And leading up to this morning, I was spending time thinking about what I would do to troubleshoot and try to figure out what was going on with this machine. I was thinking there were RAS and CAS problems to the additional RAM sockets. And when I put that RAM in there and I booted it up, and I go to About Macintosh, we now have 4 megabytes of RAM detected. So we no longer have the fault. You gotta be kidding me. And I think I figured out what was going on yesterday with it only detecting 512K and 2 megabytes of RAM. And I think it was entirely my fault. It wasn't an issue with a bad trace on the back of the board, because I didn't really touch anything other than that troubleshooting we did looking at these bad traces, which they weren't bad. I just put that nail polish over them. I think the entire problem were the RAM selection jumpers that I have installed. Yesterday I installed this blue resistor, which is on the position that says 1 row. And I lifted it from the board to do the troubleshooting. And in fact, I lifted both of these resistors, so neither of them are installed right now, which is the correct configuration for 4 megabytes of RAM. But it also theoretically would be the correct configuration for 1 megabyte of RAM, like this machine originally had when these are 256K SIMs. Well, I think the problem is when I lifted the blue resistor, I think I didn't pull it out of the board entirely. Well, I did pull it out of the board, but I think when I let go of it, I think the lead was still touching the pad. I thought I lifted it up enough, but I think it wasn't. And I think when I went and installed this additional memory, I must have jostled it and it became disconnected. So as a test, I'm just gonna rest the resistor up against the pad, just like it is there. Let's see what this does now. 2048K of RAM. You gotta be kidding me. So all the troubleshooting I did yesterday, trying to figure out what was going on with the RAM, was simply due to the fact that I installed that resistor. And if this was the motherboard with the pad right there, the little hole, when I pulled the resistor out, it was just resting against it because I didn't bend it enough out of the way. That did that. So it was entirely my doing, entirely my doing. I am curious, what if I remove that resistor while the system is actually running? Will that cause the video to stop working? Here we go, I'm just gonna bend it out of the way. There we go, it's completely bent out of the way. Yes, look what it did. But is the computer still working, I wonder? I probably should have done that while I had something running so we could hear if the sound was still working. I bet the computer is still running right now. I bet you it's not crashed. So what's happening now is a replication of the original problem we had when I started working on this system. What's happening now, and if you imagine my 4 fingers are the 1 megabyte SIMs. Originally, with that jumper in place, the system only thought it had 2 megabytes. So even though 4 was installed, the hardware on the motherboard was only addressing 2 megabytes. And the hardware, because it thought it only had 2 megs, would mirror the 2 megabytes up into the upper area as well, up to the top of the address space. So when the OS wrote to the graphics buffer in the top of the 2 megabytes, it would get mirrored up to the top, and the hardware that draws the graphics on screen is reading from up at the top. Well, when I lifted that jumper, the hardware now knows it has 4 megabytes of RAM, and the mirror went away. So the OS is still running in the lower 2 megabytes, and it's writing to the graphics buffer in this lower 2 megabytes. But the problem is, because the hardware is no longer mirroring those 2 megabytes up to the top, what we're looking at now is the contents of RAM that hasn't been erased because the ROM never knew about that additional RAM, so it never cleared it. So what we're looking at here is what was in the RAM at power up, because the graphics subsystem is still reading from the top of the 4 megabytes there. And since there's no longer a mirror, it's actually reading out of the SIMs that are installed on the motherboard. But the OS, for all it knows, it's just happily running down here in this lower 2 megabyte area. So for me, this is a good confirmation of the original problem that this machine was having. The OS does not write to the graphics buffer up at the top of the memory space, even though that would completely work no matter what RAM configuration you have. It always seems to write to the top of physical memory as dictated by the top of memory pointer that's figured out when the ROM initializes the system. And lifting that resistor has put it back to a 4 megabyte configuration, but yep, we got the corruption now because we are now looking what's in the contents of that physical memory, which was never initialized because the ROM didn't know about it. All right, just for fun, I'm going to try to reconnect the resistor. There it is. There it is. And look, just like I said, the system is still working. Just like I thought, the system is still working. Whoops. All right, well, today I learned a little bit more about the way these classic Macintoshes work. Now, as for the original issue with the graphical glitches that this machine has, I'm quite sure the problem was we had a bad connection on one of the SIMs in the upper 512K of RAM. So when the ROM tried to identify how much RAM was in the system, it was only seeing 512K, even though the jumpers on the motherboard were configured for a full 1 megabyte. And obviously the 1 meg was mostly there and mostly working, because with 1 physical megabyte of memory, like these were installed, the way the jumpers were configured or the resistors were configured on the motherboard, it was going to repeat that 4 times. And I have a feeling the ROM routines on this machine draw the Happy Mac icon, and they don't draw the gray background, they draw the disk icon up to that 3F, that top of memory space, that mirrored memory space. And because the memory was pretty much working, we did see those graphics appear. And obviously, when I was in the machine language monitor, or the Microbug it's called, and I wrote to screen page 1, that was working as well. But the OS was under the incorrect assumption that the machine only had 512K of RAM, so it was writing its graphics stuff into the top of the 512K, which was the middle of this 1 megabyte, which is not where the graphics buffer is. The graphics buffer is always at the top of the physical memory that's installed on the motherboard. If we jumped into the Microbug now, though, by pushing the interrupt button, I could still write to this physical memory because the CPU can access it, and we would be able to draw into this buffer even though the OS doesn't know about it and it isn't drawing to it. I'm still not sure why Apple didn't just write all of the graphics always to that top page of memory at 3F, because that should always work. No matter what your RAM configuration is, that would always work. Even when the OS was misdetecting the amount of memory like it was initially, we'd still have good graphics. But for whatever reason, the designers of the system software decided to write to the physical memory address and not the mirrored address, even though the graphics subsystem always reads from the mirrored address. So hopefully that all makes sense. In the end, this machine really didn't have any faults except for the fact that it was like taken apart. We had bad solder joints on the motherboard and power supply, and well, that was it. I guess we had a bad connection in the SIM socket. Now this machine is working well, other than the screen's a little bit burned in, but you know what? I've fiddled with the settings a little bit and it looks fine. It looks totally usable, and this machine just needs a little bit of a clean and it'll be all good. And I think this video really illustrates that sometimes the repairs don't always go to plan and you go down the wrong path, wild goose chases, making mistakes. It's just, it happens to the best of us. It happens to me. I know it happens to you. And that's why I like to show this stuff. And in the process, I learned a little bit more about the architecture of these original Macs. And well, when you lift resistors, make sure you pull them out of the board entirely so they're not touching the pads. Duh! Anyhow, I hope you enjoyed this video. If you did, thumbs up. If you didn't, you know what to do. I still wonder why someone left this machine in this weird, like, half put together state, but I guess maybe they didn't know about the bad solder joints. They tried to put it together, it didn't work, and they just like, oh, and they gave up on it, and then I ended up with it. Anyways, that's gonna be it. Huge thanks to my supporters, and well, stay healthy, stay safe, and I'll see you next time. Bye-bye.